Hello students, in the last section we were discussing about the degrees of freedom. It is the independent coordinates, the total number of independent coordinates which can be used to represent the motion of a body. And we told for a monoatomic molecule we have 3 degrees of freedom. Now there are 3 categories of the degrees of freedom. The first one is translational degrees of freedom, second one is rotational degrees of freedom, and third one is vibrational degrees of freedom. So translation means the motion of the body as a whole from one point to another. So here I have just given an example. Consider an oxygen molecule. It has 2 oxygen atoms which are bonded together like this. Imagine like this, here there is one oxygen, here there is another oxygen, and there is a bond. This oxygen molecule can move in the x-axis, y-axis, z-axis. So there are 3 axes in which it can move in a straight line. So the translational degree of motion is 3. That is what I have written here. The molecule which is moved to free in space needs 3 coordinates, that is in the x, y, z. So it is having 3 degrees of freedom. So that is about translational. Now consider the same oxygen molecule. I am considering the rotational degrees of freedom in that oxygen molecule. Okay, so the independent rotations that specify the orientation of a system. So already oxygen is a diatomic molecule. I told you there is one oxygen here, another oxygen here. It is fixed by a bond. This one has 2 perpendicular axes of rotation. One, it can rotate like this. This is one type of rotation. And okay, the 2 molecules can rotate like this. This is one type of rotation. Then they can rotate like this. This is another type of rotation. So there are 2 perpendicular axes that the molecule can rotate. One is like this, one is like this, and another is like this. There are 2 perpendicular axes of rotation where this oxygen molecule can rotate. So there are 2 degrees of freedom also due to rotation. So for a diatomic molecule there are 3 linear axes of rotation, that is 3 translational degrees plus 2 rotational degrees of freedom. So the total degrees of freedom for a diatomic molecule is 5. So think like this, total degrees of freedom for a monoatomic molecule is 3 because it is having only translational motion, whereas the total degrees of freedom of a diatomic molecule is 5 because it is having 3 translational motion plus 2 rotational degrees of freedom, altogether 5 degrees of freedom. Now if I take triatomic molecule, there are 2 types of triatomic molecule, linear triatomic molecule and non-linear triatomic molecule. Linear triatomic molecule means carbon dioxide, CO2, C is at the center and O will be like this. So it is a straight line molecule, linear molecule. It is having 7 degrees of freedom. Now if I take non-linear triatomic molecule, non-linear means water, H2O. So O will be here, H will be like this and like this. You know the shape of the water molecule, it is like this shape. So for the non-linear triatomic molecule, the degrees of freedom will be 6. For linear triatomic molecule, degrees of freedom will be 7. So how will be finding these degrees of freedom? There is an equation which I will tell you now. So before that I told you there are rotational, translational and one more degrees of freedom which is called vibrational. So consider the case of a diatomic molecule itself, and if I am increasing the temperature to a very high extent, then the molecules will start vibrating. The molecules can vibrate about their mean position. So there will be a vibration like this and there will be a vibration like this. So there are two vibrational motions also possible, 2 degrees of freedom due to vibration. So if vibration is also considered, then diatomic molecule will be having 7 degrees of freedom. But basically at normal temperature, diatomic molecule will be having 5 degrees of freedom. So we will be saying like this: a monoatomic molecule will be having 3 degrees of freedom, diatomic molecule is having 5 degrees of freedom, and triatomic, linear and non-linear. Triatomic non-linear will be having 6 degrees of freedom, whereas triatomic linear will be having 7 degrees of freedom. And you have to study the examples for the monoatomic molecules, diatomic and triatomic. Okay, monoatomic molecules example are all inert gases. Diatomic molecule, you know, oxygen, nitrogen, hydrogen, all those things are diatomic molecule. Non-linear triatomic. Non-linear triatomic, you can write water or sulfur dioxide. And for linear triatomic, you can write hydrogen cyanide or carbon disulfide or carbon dioxide. So please note down these examples. So we can find the degrees of freedom like this: F is equal to 3n minus k. This, using this equation, we can find the degrees of freedom easily. N is the number of molecules and k is the number of relations. I will just tell you how to make it. I take monoatomic molecule. So for a monoatomic molecule, number of molecule is 1 because it is monoatomic. Now there is no bonds or there is no interconnections because it stays as single. So k is equal to 0. Therefore degree of freedom is 3 into 1 minus 0, which is 3. So monoatomic molecule is having 3 degrees of freedom. Now diatomic. Number of molecules 2. And I told you 2 molecules are connected by 1 line. So 1 interconnection. Whether there is a single bond or a double bond or a triple bond, that doesn't matter. There is 1 interconnection between them. You can make 1 connection between them. So k is 1. So F is equal to 3 into 2 minus 1, that is 5. So diatomic molecule is having 5 degrees of freedom. Now see, third one. Triatomic linear. Linear molecule means carbon dioxide. I gave the example like that. It will be like this: carbon dioxide. You see, there are 3 atoms and this is 1 interconnection, this is another interconnection. So there are 2 interconnections between them. So n is equal to 3 and k is equal to 2. So F is equal to 3 into 3 minus 2. 3 into 3 is 9, 9 minus 2, 7. So it is having 7 degrees of freedom. Now triatomic non-linear. Triatomic non-linear, for example, it's like this. H2O. You can make 3 connections between them. 1, 2, 3. I am not talking about the bonds. You can make 3 connections between them like this. So there are 3 connections, 3 molecules. So I write n is equal to 3, k is also 3. Therefore F is equal to 3 into 3 minus 3. So degrees of freedom is 6. This is how we can find the degrees of freedom of a triatomic linear, all the molecules, whether it is diatomic or triatomic. You can find the degrees of freedom using this equation. Okay. So, we already know about specific heat. Gases has two types of specific heat at constant pressure, specific heat at constant volume, Cp and Cv. So, we studied Cp is greater than Cv. So, using this degrees of freedom, we can find the specific heat of a monoatomic gas, specific heat of diatomic gas and specific heat of triatomic gas. Okay. So, monoatomic gas is having 3 degrees of freedom. Monoatomic gas is having 3 degrees of freedom. So, how will we find the specific heat of a monoatomic gas? So, since it is having only translational degree of freedom, the maximum thing they can have is 3. Maximum degree of freedom they can have is 3. And we studied for each degree of freedom, energy per degree of freedom is half kBT, where kB is the Boltzmann's constant. Energy per degree of freedom is half kBT. kB is the Boltzmann's constant. So, if there are 3 degrees of freedom, what will be the energy? Half kBT into 3. So, it will be 3 by 2 kBT. 3 by 2 kBT. Now, using law of equipartition of energy, the total internal energy of 1 mole of gas, total internal energy is written as U. So, total energy of 1 mole of gas can be written as 3 by 2 kBT into Avogadro number. Okay, 3 by 2 kBT into Avogadro number. So, you will get 1 mole of gas. This is for 1 molecule. 3 by 2 kBT is for 1 molecule. That into Avogadro number will give you for the energy of 1 mole. Now, what is kB into Na? kB into Na. kB into Na is universal gas constant, capital R. Therefore, I wrote, instead of kB into Na, I wrote R. So, it will be 3 by 2 RT. That is internal energy. Now, specific heat capacity at constant volume, Cv, that is du by dt. So, here it is 3 by 2 RT is u, right. So, du by dt means when you differentiate, dt by dt is 1. So, you will be getting the answer as 3 by 2 R. Let that be equation 1. That is what I marked 1 here. So, Cv is equal to 3 by 2 R. Now, we studied Mayer's formula, Mayer's relation in thermodynamics, that is Cp minus Cv is equal to R. So, what is Cp? R plus Cv. That means R plus 3 by 2 R, which will be 5 by 2 R. So, you got Cv, you got Cp. What is the ratio of specific heat? Ratio of specific heat is gamma. Gamma is equal to Cp by Cv, that is 5 by 3. When you divide Cp and Cv, you will be getting 5 by 3. So, the specific ratio of specific heat, that means gamma for a monoatomic gas is 5 by 3, or its value is 1.67. You have to by heart this value, 5 by 3, or you have to by heart this as 1.67. Similarly, you can do the specific heat, ratio of specific heat for a diatomic gas and for a triatomic gas. Those things we will discuss in the next session. Thank you.